So we've talked about the semilunar valves. Now let's talk about these guys right here, okay? Generic term for them is atroventricular valves because they are from the atria and the ventricles, or they're between the atria and the ventricles. They're composed of cusps or flaps that allow the blood to flow from the atrium into the ventricles. But because of their design, just like with our semilunar valves, they prevent backflow. So on the right side of your heart, you have the tricuspid valve. So the reason that we call it that is because it has 3 sets of cusps. Even in the model, in the lab, you can see that there are 3 sets. So you've got 1 set, 2 set, 3. So we call it the tricuspid valve. On the left side, the atroventricular valve is the bicuspid valve. Bi. Why? Because instead of 3 sets of cusps, it only has 2. You've got 1 set and another set, so it's 2. Yes, I expect you to use tricuspid and bicuspid because that is technically correct. Using atroventricular is not specific enough. All right. So, pushing blood out of the ventricle causes enough pressure to push the semilunar valves open while at the same time causing the atroventricular valves to seal with the help of the chordae tendineae and the papillary muscle. As the ventricle relaxes, the semilunar valves get sucked back, effectively sealing them while the atroventricular valves open. Okay, so if you look here, here's my atroventricular valve. I've got these white cord-looking things here. These are the chordae tendineae. They are very, very strong. I had this 6'7" semi-pro football player one year, and he decided he was gonna tear it apart with his bare hands. He couldn't do it. And I'm telling you, this guy was like 270 and all muscle, and he couldn't do it. So they're pretty darn strong. Now, these white things are basically anchored to these muscles here. See how they look like fingers? They're called papillary muscles because they look like fingers, okay? So you've got the papillary muscle, and when this relaxes, it causes this valve to open. Now, everybody probably knows what a baby snot sucker is, right? How does it work? Well, it works because it creates suction, right? When your heart relaxes, it's kind of like the baby snot sucker, and it causes kind of a vacuum and a suction. When that happens, it actually pulls this aortic semilunar valve back and causes it to seal, while at the same time causing this one to open. Now, when it contracts, okay, it forces the blood through here, through the semilunar valve. The thing is, remember these muscles here? When your heart contracts and that muscle contracts, it actually pulls a little on those chordae tendineae. So when the blood flows this direction, these atroventricular valves actually kind of puff up like a parachute. Think about a parachute for a second. Any video that you've seen with a parachute, it's kind of floppy until it catches air, and then it goes and it really, really catches air and seals, right? Okay, with these, it's kind of the same thing. They get yanked on as the blood pushes, but as the blood pushes, it fills them up, basically sealing them so that blood flow can't go backwards. And there's a video on one of your quizzes that actually has that, and it shows that kind of sealing and opening and sealing and opening. Okay. So the route of blood flow through the heart. Normally, I go through this step by step and draw it out and everything. So I'm going to use the one that I did for my lab, and I'm going to upload that along with this to kind of help kind of take you step by step. So this is what your book has as far as how the blood flows through your heart. Every circle is a valve. The rectangles are going to be the chambers. The beige, I guess, is going to be the tissues. And you can see some are blue, some are red, meaning deoxygenated blood, oxygenated blood. I said this earlier. Arteries carry blood away from the heart. Veins carry blood toward the heart. Blue always means deoxygenated. Red always means oxygenated. So I've got the right atrium, the left atrium, the right ventricle, the left ventricle. This is not anatomically correct. So yeah, don't quote me on it. Body tissue, lung tissue, because these are our two circulations, systemic and pulmonary. You've got your valves, the bicuspid in the left, the tricuspid in the right, pulmonary semilunar in the right, aortic in the left. You've got the aortic valve going to the aorta, the pulmonary semilunar valve leading to the pulmonary trunk, which splits into the pulmonary arteries, comes back through the pulmonary veins. The aorta splits into the coronary arteries, which you can't see at all. Okay, can you see that at all? No. Hang on. See if I turn this off, if that'll work. Actually, this might work. Maybe. Okay. Yes. Oi. Okay. So you got the aorta. You've got the aorta splitting into the coronary arteries. You've got it continuing to the body. And then in the body, you've got the upper portion of the body above the heart being drained by the superior vena cava, the portion below the heart being drained by the inferior vena cava, and then the heart tissue itself being drained by the coronary sinus. Again, not anatomically correct, but I'm not that good of an artist, so you're just going to have to put up with it. The thing about the cardiac cycle is it is a cycle. You can literally start anywhere. It doesn't matter where you start, and it's always going to come back to where you started because it's a cycle, okay? I always start here, though, because it's just the way I learned it. So, deoxygenated blood drains into the right atrium via the inferior vena cava, drains the lower body tissue, which you can see there. The superior vena cava drains the upper body tissue, which you can see there. And then the coronary sinus drains the heart tissue, which you can see there. The right atrium fills with deoxygenated blood. Ta-da! Deoxygenated blood goes from the right atrium through the tricuspid valve into the right ventricle. The right ventricle fills. The right ventricle squeezes and pushes it through the pulmonary semilunar valve into the pulmonary trunk. Again, deoxygenated blood, you can see that it's blue. The pulmonary trunk splits into the pulmonary arteries, a right and a left pulmonary artery going to the right and the left lung respectively. Basically meaning, since I said right and left, the right goes with the right, the left goes with the left. In the lungs, we exchange carbon dioxide for oxygen, and the blood returns to the left atrium via the pulmonary veins. Left atrium fills with oxygenated blood. Again, you can see it's red now. I hope. Maybe. Scoot this up a little. All right. All right, so the left atrium squeezes the blood through the bicuspid valve into the left ventricle. Left ventricle fills with freshly oxygenated blood. Now, the left ventricle squeezes the blood through the aortic semilunar valve into the aorta, which splits into the coronary arteries, carrying oxygen to the heart tissue, and then continues to the body to basically give the body tissue oxygen. Again, I'm going to post that other video. I'm going through it pretty quick right now, but understand me drawing it and going through it again, you'll see it, okay? So histology. What's histology? Histo means tissues. Ology means the study of. So histology is the study of tissues. So your heart consists of a plate of fibrous connective tissue. See the white? This is your heart skeleton. It is harder than the muscle. And actually, it kind of sounds when you're dissecting a heart like you're crunching through cartilage. Okay, that's how sturdy this is. This heart skeleton actually has 3 jobs in your heart. It supports the semilunar and the atroventricular valves. So you go to Whataburger, you get yourself a chocolate shake, and it's really, really thick, right? So you take your shake and you go, what happens eventually? Right? It collapses. And the reason that happens is because you're creating a vacuum. By putting so much suction, you're sucking all the air out and there's nothing to replace it since the shake isn't moving. So it basically sucks all the air out and pushes the sides together. Your heart works based on pressures. Different pressures cause things to eject from it or fill up. So if I'm doing that, it's kind of the same concept as the Whataburger straw. If I'm changing pressures, there's a real good chance if I don't have support around that valve, it's going to and seal. So you've got this heart skeleton. The heart skeleton gives it enough support so that even though there are changes in pressure, it's never going to collapse like that. So that's one function. It acts as electrical insulation between the atria and the ventricles. So if you think about it, I need the atria to completely empty into the ventricles so that they fill up. So when they squeeze, they're actually squeezing a good amount of blood out. So the electrical signal that goes down the heart actually slows when it hits this cytoskeleton or heart skeleton. Cyto means cell, that's not the same thing. Okay, so when it hits it, it kind of slows that signal down enough to give the atria enough time to finish squeezing to empty into the ventricles. So it is electrical insulation. It slows that signal down slightly so that it can actually move the way we need it to move. And finally, it acts as a point of attachment for muscles. So it's the heart skeleton. Your skeleton, your bony skeleton, actually does the exact same thing. It acts as an attachment point for your skeletal muscle. Yeah? So this skeleton actually acts as an attachment point for that cardiac muscle so that it has something to pull against so that it beats. Now, something else I want to mention, because I think I forgot to say this earlier. Your heart beats top and bottom, top and bottom, top and bottom. The way that I explained it, it seems like the right side goes first and then the left side, but that's not how it works. In fact, it looks like it's twisting and it's twisting top and bottom. If you've ever seen a video of a heart on YouTube or in a medical show, it really does look like it's going and the reason is because the top chambers contract at the same time and the bottom chambers contract at the same time. Okay. So cardiac muscle itself, you've got these elongated branching cells with 1, maybe 2 centrally located nuclei. Functionally, it is very similar to skeletal muscle. You've got the actin and myosin that are crawling on each other to contract, and you've got them forming the sarcomeres, the same thing you saw in chapter 9. The arrangement of the smooth endoplasmic reticulum and the transverse tubules is different, but The function of them is essentially the same. So remember in chapter 9, I talked about actin and I talked about myosin, and I said they crawl on each other. They make the muscle shorter. When they let go, your muscle relaxes. So you basically have that same concept in cardiac muscle. The actin and myosin are still interacting to cause that contraction. When they let go, it relaxes. Same. Now, the cardiac muscles are joined by something called intercalated discs. They allow the movement of that sodium for the action potential to move directly from one cell to the next. Thus, the cardiac muscle cells function as a unit. Intercalated discs are a combination of desmosomes, which hold the cells together, and gap junctions, which allow material to basically flow between cells. Something else you have to understand about the heart. Your heart has to contract in sequence, okay? Literally, it's like a line of dominoes. I've got to have cells A contracting, followed by B, followed by C, followed by D. It has to happen in sequence. If it doesn't, your heart ends up doing this business where it's just kind of randomly contracting. If that happens, you die. So not a good idea. So I have desmosomes that basically help to hold the cells together so that I can contract and I can expand, but the cells aren't going to fall apart. And then in between the cells, I have tubes, basically the gap junctions. And once I start an electrical signal, my sodium moving to cause depolarization up here in these cells at the top of the heart, it can literally just flow down almost like a waterfall into the next set of cells, into the next set of cells, into the next set of cells, guaranteeing that I'm actually going to have the contraction in the sequence I want it in. Okay, so cardiac muscles have a slow onset as well as period of contraction due to calcium movement along the myofibrils. It has a good blood supply, which supports aerobic respiration, basically ATP production with oxygen, and I can use multiple fuel sources. I can use glucose, I can use fatty acids, I can use lactic acid. Something that's interesting, cardiac muscle does not develop oxygen debt. So you know how you go to the gym and you work out really, really hard and you come back the next day and you're like, I can't move my arms, right? That happens because of oxygen debt. Basically, you run out of oxygen in those cells, in those muscles. So they switch to another kind of respiration, anaerobic respiration. They create a whole bunch of lactic acid, which basically means your muscles are soaking in lactic acid. Your heart never does that, not ever. Now, something different. So your skeletal muscle is just used to move your limbs. That's all we're doing. We're not emptying volumes. We're not doing anything like that. Your heart is moving volumes of blood. I have to give it enough time to contract and empty before I can get this part of my heart to contract. Okay? So in a way, cardiac muscle is slower in what it does because I'm moving volumes. I'm not just moving the heart from point A to point B. I'm actually having to shift volumes from the atria to the ventricles to the body to the lungs. And that takes a bit of time. And I have to kind of account for that because if my heart were to beat really, really fast, that's bad because literally, one, I'm not giving it enough time to fill back up with blood. It would be like, trying to put gas in my car and going, okay, I'm gonna put gas in my car. Okay, I'm done. You wouldn't put gas in your car that fast. There's no way. You have to the kink, right? There's that time frame for the fluid to actually transfer from the pump into your tank. Same here. If you've got somebody and their heart is going so fast that there's not enough time for fluid to fill the chambers, they're going to die, okay? Because blood isn't being pumped anywhere because there isn't enough time for it to actually fill any of the chambers at all, okay? So keep that in mind as well. All right, so we have a conducting system in the heart. There's an electrical system in our heart. It actually does consist of modified cardiac muscle cells, and there are two primary nodes, two primary bundles, a conducting bundle, and both are made up of very small diameter cells. Why? It slows everything down. Remember about the whole, I've got to be able to fill up and empty? So the first node that we have, or bundle of nervous tissue, is the sinoatrial node, which is right here. Then we've got the atroventricular node here. This one fires and it basically spreads across both atria. Then it goes to the atroventricular node. The SA node, the sinoatrial node, is usually the one that initiates action potentials and causes it to spread around or across the atria, causing them to contract. At the atroventricular node here, the action potential slows down. I have to allow it to slow down so I can finish emptying these guys. If these guys start to contract too fast, either all of these valves are going to close or I'm not really going to empty these atria. So kind of going and then allows this to finish its contraction before moving down here into the ventricles. So it goes from the atroventricular node into this atroventricular bundle, the AV bundle, that splits into the left and right bundle branches, and then it comes up through the Purkinje fibers here. Now, something interesting, think about it. This is the chamber we're trying to empty. These ventricles have to contract from the bottom up. It has to go that way so that this blood gets squeezed out. If you start at the top and come down, then you're basically pushing the blood in the wrong direction, okay? So we've got the Purkinje fibers causing the contraction of the ventricles from the apex, the point, up toward the middle, okay? So SA node to AV node, AV bundle, right and left bundle branches to Purkinje fibers. So the electrical properties of your heart, you've got action potentials, autorhythmicity, refractory periods, electrocardiogram. So cardiac muscles have a resting membrane potential, just like a neuron, just like skeletal muscle. But it does depend on the permeability, how permeable the plasma membrane is. Normally, in a resting heart cell, you have low permeability to sodium and calcium. If you have a resting cell, sodium and calcium are not moving very much at all. They're just not moving. There is a higher permeability to potassium, but once threshold is reached, you get an action potential. So we talked about this in a huge amount of detail with chapter 9 and chapter 11. These cells, if they're resting membrane potential, the only thing moving in and out of them at all, in any great abundance, is potassium. So sodium and calcium, not really moving, okay? Now, the action potential, that all or none point. When I talked about this in AMP1, I talked about a gun. And I said that there's a point where you're pulling the trigger where you can't take it back. You're going to get an action potential. You're going to get that gun to fire. It's not like if I go and then I let go of the trigger, the bullet's going to go and suck back into the gun, right? That's not the way it works. When you pull that trigger, you get to that all or none point where the hammer's going to hit the back of that bullet and it's going to go, right? In an electrically excitable cell, like a cardiac muscle cell, there's a certain amount of change in charge that happens in that cell. And once that point is reached, it's called threshold. And when you reach threshold, that muscle cell is going to contract and you can't take it back. Okay? So this is a graph of a muscle cell contraction. And you'll notice, compared to a skeletal muscle contraction, this is very, very different. You actually have 3 phases, 4 technically, but 3 phases. You've got the depolarization phase, the early repolarization, go back, dun, 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 early repolarization and plateau, and the final repolarization. Okay, so depolarization, the inside of my cell becomes more positive very quickly. How do I do that in a cardiac muscle cell? Well, part of this is very familiar. Voltage-gated sodium channels open. Sodium rushes into the cell. That's part of the reason why the inside of my cell has become more positive. The potassium channels actually close. Now remember, potassium is the thing that should be able to move back and forth regardless, because potassium is supposed to easily be able to move. And I'm sealing those doors, not letting potassium go anywhere. Now, something else that's a bit different from skeletal muscle. I have voltage-gated calcium channels also opening. So not only do I have sodium flooding into my cell, now I've got calcium flooding into my cell. Sodium is 1 positive, calcium is 2 positive. And all of those positive basically flowing into my cell are causing the inside of my cell to become more positive. Now, if you look, this is depolarization. And at number 2, I've kind of got a 2-step thing going. I've got early repolarization where it looks like it's going to come down, but it doesn't. It ends up plateauing where it kind of just stays the same here. Excuse me, right? So the first thing that happens in that early repolarization is that the voltage-gated calcium channels that allowed all that sodium channels that allowed all that sodium in close. So no more sodium is moving. Some of the voltage-gated potassium channels open. So remember, potassium can move, and it's usually higher inside of my cell. So if they open, potassium's going to start leaving. Sodium that's positive was supposed to be coming in and now isn't, and that positive potassium is now leaving. So I'm losing positives. That's going to bring me down. But remember those calcium channels I was talking about? They stay open, and eventually the positives from my calcium coming in are going to equal the positives from my potassium going out. So I've got the same number coming in as I've got going out, and you hit that plateau phase where you're not really changing the charge because you've got the same number of positives coming as going. Now, this final repolarization right here, number 3. Remember those voltage-gated calcium channels that stayed open here? Yes? They're going to close. And I've already closed my sodium channels. Those are closed. I'm closing the calcium channels. And in the second step, I open some potassium channels, allowing potassium out. Here, I'm opening a ton of potassium channels. So now potassium is just flowing out of my cell. That's going to take that plateau phase and make it go funk and come right back down, because the inside of my cell is becoming more negative because I'm losing all of those positive potassiums. Now, something kind of interesting. Cardiac muscle versus skeletal muscle. In skeletal muscle, action potentials like this take about 2 milliseconds, 500th of a second, okay? 1/500th of a second. Whereas cardiac muscle takes 200 to 500 milliseconds. Remember, we're moving volume. If we're moving volume, then yeah, we've got to have that kind of slow, I want you to contract, and I want you to relax, as opposed to and you're done. Because, again, what am I moving with my heart? What am I moving with my heart? Volume. If I'm moving volume, I can't count on my heart going really, really quickly because then there isn't enough time to actually shift volume from one chamber to the next. So that slow onset, the plateau phase, all of that just kind of gives me a little bit more time to finish things before I start something new. Okay. Okay. Oh, actually, that catches me up to the second video that I posted as the first video. So yeah, that's where we end. Sorry about that, guys. I had already deleted the other videos, so I will try and get these posted as quickly as possible. And again, I apologize. I'm sorry about that.